Um, hello, hello. So this is part two to the revision session stream, video, whatever you want to call it, I did yesterday. Um, uh, because it's split in two, I think the plan is, especially for YouTube anyway, when I upload it, I'll upload this part two on its own, but then I'm going to put part one and part two together as one. So if you're watching the combined video, this will probably be like in the middle, and it'd be like a weird, like, I don't know, transition between the questions. But this is the second part of the session. And yeah, I'm just going to probably get started then, because I said everything I need to say yesterday. So I'll just get cracking. Also, oh yeah, last thing, the predicted topic, I did go over it yesterday, but it will be in the description if you're on YouTube anyway. If you want to check that out, those are the topics that haven't been assessed yet and are likely to come up based on past papers. Okay, but let's have a look at this question then. So it says Pfizer is studying the population of rabbits in the park. She wants to estimate the number of rabbits in the park. On Monday, she captured a random sample of 20 rabbits in the park, marks each rabbit with a tag, and releases them back into the park. On Tuesday, then she captured another sample of 42, and 12 of the rabbits are marked with a tag. Can find an estimate for the number of rabbits in the park. So this is a kind of typical capture oh, recapture method capture question, which means essentially we have one sample of something. Here we have rabbits. We tag them, and then we recapture. Then we get another sample, and we then recapture some of the rabbits we tagged. Okay, and from that we can estimate the total population. So the rabbits in the park. And the key assumption with this question is because it's an estimate, so we're going to make an assumption here, and what we're going to assume is actually in both of these samples, the proportion of how many rabbits were tagged to how many there are is proportional in both of them. So what does this mean? So um in the first sample, um we obviously out of a total population of rabbits. So say we had say in total there are n rabbits, right? In the park. That is actually the total. That's what we want to find out. This n. We want to find out the number in the park in total. And from the n, we have tagged 20 rabbits. So that's saying 20 out of the total we have are tagged. Now, because of our assumption, we're assuming the amount of tagged is proportional in both of them. Well, in this case, in them, in then we have another sample, and the total number of rabbits is 42, and out of the 42, 12 of them are tagged. Okay, so that means actually the amount of tagged out of the total number, well, it's going to be 12 out of 42, isn't it? And that is the central idea of these sort of questions. So I guess just reiterate once more. In the first instance, out of the total amount of rabbits in the forest, we tag 20 of them. And so that's where we get this sort of ratio proportion from. So out of the total number of rabbits, we tag 20. And then we get another sample, and then in total there's 42, and 12 out of the 42 were tagged. And so these two are the same because we're assuming that the sort of proportion or the amount or the fraction or percentage of the rabbits we have that are tagged is the same as any sample we take. So we get this, and this is an equation. You can alternatively say n over 20. So you could say, well, we have the total amount of rabbits, and then we tag 20. That's going to be the same as the total in the second sample over how many tag in the second sample, and Tuesdays out of 12. That just comes from obviously flipping the fractions. But no matter how you see it, you should get to this sort of expression, right? This sort of equation. And so we said n is the total amount in the park, which is what we want. And so we just need to solve for n. Therefore, if we cross multiply, so the 42 is going to times by the 20, and the n is going to times by the 12. So 12n, 12 lots of n is going to be 42 times 20. And then we can simplify it a little bit. So in the calculator, 42 times 20 is going to be 840. And then therefore, to just get n, we're going to divide by 12, right? To undo the 12. So n is then going to be 840 over 12. Therefore, n is going to be 70. Okay. And that would be the total in the park, right? Because that's the whole idea, right? So from the total, so the whole idea of these sort of questions is we have the total population and we take a sample of them to tag. So in this case, out the total, we take 20 rabbits to tag. Then in another instance, then we take another batch of rabbits, and then we see how many were tagged after they spread out and mixed. So you get some rabbits that are tagged, and then some that are not. And then in total, then you get some sort of proportion that are tagged out of the total you have, and therefore you can estimate the total amount of rabbits originally. Okay, hopefully that made sense. That is really the core idea of these sort of capture-recapture questions. And yeah, hopefully the sort of logic behind that kind of makes sense. Okay, then it says LB. He's studying the population of rabbits in a wood. One day he catches 55 rabbits and finds 40 of these rabbits are marked with a tag. LB estimates there are 50 rabbits in the wood. Explain why his estimate cannot be correct. Okay, so it's only one mark. I wouldn't think too deeply about this. But remember, what it's saying is when we're tagging a rabbit, we, we're estimating the total population, right? So that means really we're saying 55 rabbits have to be less than 50. But that's not really what's going on. That it can't be right. If he's capturing more rabbits than 50, well, how can there be less than 55 rabbits in the forest or the wood? You know, the whole idea is that when you take a sample, so here, sample 42, there's not going to be less than 42 rabbits, is there? Where are the rabbits coming from? You know, so actually, I guess, kind of on, not obviously, but I guess, kind of on the surface, right? Don't think too deeply. She's really just saying that she there's less rabbits than the amount she's captured. Really, how's that? You know, um, she's captured more rabbits than 50. So how can there be less than 55 rabbits in the wood? So therefore, she cannot be correct. So not correct. Since 50 is less than 55. So she's saying there's less rabbits than L be captured. Did I call it a she? Is it he? Doesn't really matter. Then L be captured, which is nonsensical, right? There's less rabbits than L be captured. And yeah, so hopefully, again, kind of wrap your head around that. Because the whole idea is that actually with these sort of sampling ones as well, the number of rabbits is going to be too big, right, to count all of them, right? So then, therefore, we tag some of them and then we collect a smaller sample. So here we have 42, but originally there's 70. So we create a smaller sample, and that's the whole idea. From this smaller sample, we can then estimate the larger end population because of the fact we can't physically count, how many there are in total. And actually, this isn't the best sort of example because 70. If you're going to capture 42, you can probably capture all 70. Well, unless the rabbits are just hard. Some of them are hard to see, not hard to see, but they're hide. But say, for example, 42, but then there were like 2,500 rabbits, which I think in total. You're gonna what it makes a lot more sense to just estimate and take a sample. So then with this example, she's captured. So the whole idea is you take a sample 55, so then the total population should be more than 55 because it's the whole idea of the sample to avoid calculating or counting that many amount of rabbits, how many there might be. So saying there's less rabbits than the amount we have, it's just it's just it can't be right. It's nonsensical. Um, but yeah. Another question it might come up, potentially sort of question they might ask, what assumptions did you make? Because it says it's an estimate. Um, did you make with your calculation or something like that? And the whole idea is you're saying that essentially it's the amount for any sample you take, the amount of tagged rabbits is proportional to the total population. But that necessarily isn't the case. They're not going to be that well distributed. You might just get lucky and get most of the tagged rabbits. But actually, there might be a lot more non-tagged rabbits, or so. Therefore, the assumption might not be right because it might not happen in reality. That it's proportional, right? It might not happen in reality. So the assumption we made was we assume uh, the proportion of tagged rabbits is always the same for any sample of rabbits we take. Okay, so that would be the assumption, right? Obviously, whatever question I might throw at you, obviously rabbits change to whatever. If they ask for kangaroos, if they ask for monkeys, if they ask for whatever, you can just obviously change the rabbit bit. But that is the general assumption with these sort of questions. They might ask a one marker, asking what assumption did you make, or how could this affect your answer because of this assumption, something like that. They might potentially ask it, but that is what you'd kind of need to get at. You're assuming so the proportion of the tagged rabbits compared to the total population or the total number of rabbits you have is always going to be the same, which is why we get this equation. Okay. But yeah, I'm going to move on then. Question 16. Okay, so we are given. Well, we don't need to. So given A and C are points on the circle, and AB and BC are tangents. So that's going to be this line here and that line there. Okay. We need to prove that triangle ABO, so that's going to be that triangle there, is congruent to triangle BCO, which is going to be that triangle there. Okay, so um, generally when you're proving congruency, there's certain ways you can do it. Angle side, either angle side, so two angles on the side are the same, or one angle and two sides are the same. Oh, ass. Probably let's call it SAS. Or three sides are the same. Um, or you got a right angle triangle, and the right angle they both have a right angle. They both have the same hypotenuse and another side the same. Okay. Um, which is basically just a form of SAS, right? And the hypotenuse is another side, right? But those are the four. But you kind of angle, because they will be similar if all three angles are the same. But they would still their lengths will vary by scale factor. They won't be exactly the same. So, for example, if we had like I don't know, 90 and then 40, and then what the other one? 90, like 50. These aren't the right numbers. I'm just throwing some out there to prove a point. So say we have two. Actually, no. Let's say five, 3 and 4. Um, if they have the same angle, say here 40, 50, and right angle, same angle, but you can still form a triangle by just scaling it. So we could have, for example, times by 2, we could have like 10, 8, and 6. Okay, they vary by the same scale factor, but they're not exactly the same triangle because the lengths do not have to be the same. So that's really the only thing you have to be aware of is not make all three angles the same, right? Anything else, any combination of sides of angles, otherwise if you get to one of them, then you've got your proof. Okay, so you just need three bits of information that I was saying. But let's have a go for it then. So we need to prove this triangle. This top one is the same as this one. So we're going to need either three combination of angles or sides the same. Okay, so actually notice because it's with circles, we're probably going to need our circle theorem, and the thing that gives it away is the fact we have a tangent to a circle, and we also have a center as well. So that hints that we might need to use some circle theorems here. Okay, so the first one, so when you're given the tangent to a circle, really there's only two circle theorems that should scream to you. Either the alternate segment theorem, where we need a chord, or the fact that the radius is perpendicular to the tangent, right? Um, but here we don't. There's not really alternate angle. Are we creating any segments? No. Um, because bear in mind a segment is formed by a chord that goes exactly from one point of circumference to the other. This here is only half of like a half a line. It's not going from one point to circumference to another. Because obviously in here the line bends, so it's two different lines, right? So none of these are chords. This line or the so the only theorem we can use is uh the um the fact that tangent's perpendicular to the radius. So do we have a radii? Yes, we do, because we also told it's the center. Um, so what does that mean then? Well, this has to be a right angle, so does this. Cool. So therefore, angle um, uh, BAO equals angle BCO, which is 90. And the reason for that is going to be since the radius is perpendicular. And hopefully you can see that they are radii because this is going from the center to the circumference, right? So it is a radii. So the radius perpendicular to the tangent, right? Cool. So we've got one angle out the way. But actually, we also know a side as well because this side here is going to be the same as this because they're both radii. They're both a radius. So radii is a plural of radius. But if they're both the radius of the circle, they're both the same length, so they're the same. So therefore, length side AO uh, is equal to side CO, or you could call it OC or OA. It doesn't really matter. As both are radii, oh, so both are the same length. Cool. So now we just need one other bit of information. Well, actually, this side is going to be there as well. This line BO, because this line is going to be common to both triangles. right? So therefore, we could say that side BO is common to both triangles. And actually, what we've got there then is that two sides are the same, and and we've got a right angle. And actually, more specifically, this side here that we just did, that's the hypotenuse, right? Because it's opposite to the right angle on both of them. So actually, we actually got RHS, haven't we? Where we've got a right angle that's in both the triangles. We've got a hypotenuse that's the same because the hypotenuse is on both the triangles. They're common, as we just saw here, and one of the sides are the same as well, which is the radii. Okay, so actually, therefore, ABO is congruent um, to BCO, the triangles, by RHS. And I think you should be fine by just abbreviating that. You know what? I will double check the mark scheme, but they will recognise common like acronyms. So I think you'll be fine. But let me just double check. But alternatively, I believe you actually could also deduce that two of the sides are the same, but then this side will be the same as well. Let me get rid of that. But this side will be the same as well because remember, there's another circle theorem where, and actually, you could kind of use it to prove this, couldn't you? I think you'd prove this could kind of be a proof of circle theorem because now that we know they're congruent, we know by really this side here on the tangent has to be equal in length to this side, right? And actually, that also stems from the circle theorem where what's it called? Where that if you have two different tangents to a circle and they both come from the same point B, then they're equal in length. Okay, which is exactly what I got here. They're both tangents and they both come from the same point, so therefore they're the same in length. And then therefore three sides are the same, so you'd prove it by SSS, or you could have SAS, or whatever combination you have. So you have three. So yeah, that's the proof for that. Quite a really nice question, I think, and also like I said, they do like to link multiple topics together. So they could, for example, here link like congruent triangle proofs to circle theorems, right? Um, and yeah, that's not too bad in my opinion. There isn't really a mark scheme for this because it wasn't from a past paper. It's from the topic question sheet from for congruent triangles, which you can find on Maths Genie. Um, but it could absolutely be on the question paper. Okay, so hopefully it made sense. Question 17. Okay, this is iteration. Now I know there was a slightly different iteration that came up on paper 2, but it looked something like this, where like you had KN. No, sorry. You had PN, for example, was KPN minus PN plus 1 was KPN. And then you have to kind of use it to get the first few values of n. But the one here, this is probably going to be different, a different iteration question, but it could still come up. And I think they're going to ask this because they love it because they can ask you to rearrange stuff as well. I remember rearranging equations haven't explicitly come up yet for higher tier, so they can link multiple topics at once. Okay, so let's have a go at this then. So again, this is very, very standard sort of question. So part A firstly says show that the equation has a solution between x is 1 and x is 2. Okay, this isn't I don't think there's many examples of this, but it's good to go over in case it comes up anyway. So the procedure is when we rearrange an equation to equal 0, you then substitute, if you think there's a solution between two values, so here, you substitute both the values in. So I'm going to say sub x is 1, then we're going to have 1 cubed, 2 to the 1 minus 6. And, so that's going to equal, if you put that into the calculator, -3. So it's not a root, but it's not too close to 0, I guess. Then we're going to sub the other value in. So x is 2. So then we're going to get 2 cubed, add 2 lots of 2, minus 6. And that's going to be 6. Okay. And so what we notice here is there's a sign change. So what that's essentially saying is this function here. Well, x is 1 is -3. And then at 2, it goes to 6. So what's saying is, oh, that at some point between 1 and 2, because this is going from negative to a positive, or vice versa, it has to pass through the x-axis, which you should know corresponds to a root. So when it equals 0, but you don't have to show any of it. That's the idea behind it. So at GCSE anyway, then you need to just say, well, there is a sign change between x is 1 and x is 2. Therefore, there is a solution between x is 1 and x is 2. For GCSE, you'd be fine to say that, right? Hopefully, that again, this sort of idea behind that makes sense. But for GCSE, you'd be fine for just doing that, okay? Okay, so then part B, and also you can kind of see, well, because it's going from -3 to 6, well, it's going to have to go to every value in between, but 0 is in between -3 and 6, so therefore you're going to get 0 at some point. But anyway, that's the idea behind that. So let's have a look at part B. Then it says show that the equation can be rearranged to give x as this. Okay, so again, this is rearranging stuff, which they might ask as well. So we kind of need to look at this form here. So how? So okay. So firstly, I notice it has to equal 6 over something. So I think it's a good idea to first say x cubed plus 2x is going to equal 6. Okay. Then I notice, well, we actually have an x squared. How are we going to get x squared? But also notice I can factorize, can't I? So then I can say x of x squared at 2 equals 6. And therefore we've got a match, right? Therefore we can say x then is going to be 6 over x squared at 2. And there we go, got our answer. And so yeah, so the idea was you could rearrange one of the x's. So you could say x cubed was 6 minus 2x and then cube root it. Or 2x would be 6 minus x cubed. But here you need to pay attention. We have an x squared, which can only come from factorizing. But yeah, I think that's a really hard one actually. And most of the time it's fairly obvious. Usually they'll probably just say x is like the cube root of 6 minus 2x, which comes from putting x cubed is equal to 6 minus 2x and then cube rooting. But this one's quite nasty. But that comes from factorizing. And yeah, so I think the key giveaway is that we have to have x equal to 6 firstly here. So I'm just going to put 6 on the right hand side. Then I can see what to do with the x. And I can factorize and then divide. And then there we go. But that's only 1 mark. Okay. So then part C says, starting with x0 is 1.5, use the iteration formula twice to find an estimate from the solution. Give it to 4 decimal places. Okay. So we need to use it twice. So xn plus 1 is 6 over xn squared of 2. So that's just me copying it down. So if I notice here, to get if I plug x0 given into here, Then the next term's going to be x1, right? So that means the next term x1 is going to be 6 over x0 squared, add 2. But that's going to be 6 over, well, x0 squared, well, that's 1.45 squared, add 2. And so I'm going to do it over here. Then x1, if we put that into a calculator, that's going to be 6 over 1.45 squared, add 2. That's going to be this number here. And you will just have to write all the numbers down, unfortunately, in your calculator. So I'll get 1.4625228852. Okay. You have to write all the places because this sort of question, as you know, 4 decimal places are a lot of decimal places. It really is important to show all the digits with this sort of question. So you do have to write them all down. But then therefore x2 then. Well, I'm not gonna show the substitution this time. But what I'm gonna say, well, I'm gonna plug then the previous answer x1 into here, right? Into xn, and then to get x2 back. So then if I do x2, that's going to be, if I put that into the calculator, 6 over the previous answer squared, add 2, and then I get x2 is 1.44963, 4937, which to show what I've done, I've said x2 was 6 over 1.4625, whatever I got at this number, all squared at 2. Okay, and that's what I put into the calculator, and then they get this number back. Okay, but as for getting the marks, you only need to show the substitution like I've done here for the first value. Then the examiner would know what you're doing to get the other values, right? Only do it once, and then you can just click your calculator to get the other value. But I only said use it twice, so I've used it twice now. So actually, this is the answer, our estimate. So therefore, we need to round it to 4 dp, decimal places. So 1.4496, that's the 4th decimal place. Then 3 is less than 5, so we keep it where it is. So it's going to be 1.4496. Looks like we're carrying decimals, doesn't it? 4496 to 4 dp, and that is our answer. Cool. So it's a very standard question, right? I've never seen them overcomplicate this. It always looks the same. The rearranging bit might not be the best sometimes, like here, but eight's only 1 mark, and B, again, there's not much you can do there, so it still shouldn't be too bad. But yeah, just remember this sign change could be an easy 2 marks, right? But if you've not seen it before, please learn how this works now. So just plug the 2 values in, then there should be a sign change, and therefore there's a solution. Okay, and then obviously this is very formulaic. It's the same process every time. So you use the formula to get the next value for x, and then use it again to get the next value, and so on until you get it to how many times it asks. So here it's 2 times, so we get x2. Okay. But yeah, cool. Okay, question 18. Again, this comes up every year, like some sort of simplifying algebraic fractions. But this time we need to show that 6x cubed over 9x squared minus 44 divided by 2x to the 4 over 3 lots of x minus 4 has to simplify to this. Okay, so we need to work with this then. Well, the main step with these sort of questions is you need to factorize anything you can. So obviously the x cubed won't factorize, the x to the 4 won't. This is already factorized to 3x minus 4, but does this? And actually, you should notice that this is the difference of 2 squares. So 9x squared minus 144. 9 is 3 squared, and 144 is 12 squared, right? Therefore, this will go to 3x minus 12 and 3x plus 12, right? Remember the general completing the square of a squared minus b squared is a minus b, a plus b, okay? And here a would be 3x, okay? And b would be 12. Okay. So then I can factorize it to make my life easier. So that'd be 6x cubed over 3x minus 12, 3x plus 12. Okay, and now I'm dividing. So when you divide two fractions, like with any fraction, you should remember KFC or you keep flip change. But so what that means is you keep the first fraction the same, like we've done, then you change the sign, so it becomes a times, and then you flip the fraction. So 3x minus 4 over 2x to the 4. We're going to go over here. Well, then you just, at this point, when you times two fractions, you just times the numbers across. So you times the numerators to get 6x cubed times by 3 lots of x minus 4. And then you times the denominator, the bottom numbers. So it's going to be 3x minus 12, 3x plus 12, times by 2x to the 4. Okay, and then we just need to simplify this. So firstly, I notice, again, by index laws, the x cubed will cancel with x to the 4, and x cubed over x to the 4 will just go to 1 over x, okay? Because then you're doing 3 minus 4, which would be x to the minus 1, so only x there, okay? You can also visualize this as saying, this is times at x 3 times, and then x to the 4 times it 4 times. Wow, the first 3 cancel with the bottom 3, and then you're left with 1 over x. So you got 2x then. Then I know, wow, well, I also see that the 6 will cancel the 2 here, because 2 goes into 6, and actually 6 divided by 2 is then 3, right? So then I'm left with 3 times 3. Let's do it here. I'm left with 3 times 3 lots of x minus 4 over 3x minus 12, 3x plus 12 times by nothing, right? Just times by 1. But times by 1 is itself, really. Because all of this is cancelled, remember? Oh no, we left with x, sorry. Because x cubed you cancelled, well, because remember we cancelled the 4 and we cancelled the 2, but we're left with an x, right? Because of this, right? So we have an x on the bottom left. So that's what we're left with. Okay, so, but we, at the moment, it's not looking like this form here because we have 2 brackets, not 1. So notice we have x plus r, but we have 2 brackets and then another x. So how are we going to deal with that? We're going to need to simplify some more. So we need to see what else we can factorize then. Okay, well, I then notice, well, actually, 3 is common. 3 we can pull out, can't we? So in this, 3 times 3, first of all, on the top is going to be 9. And that's going to be log not x minus 4. Okay, then I have, well then, well the 3 here, we can pull a 3 out of both terms, 3x minus 12. So then we could say that's 3 lots of x minus 4, because then that would go to 3x minus 12, right, which is what I've got. So notice we can pull a 3 out there, okay? And then what about this one? Well, this one we could do the same. We can then factorize it further to get another 3 out of there. So it's going to be times by another 3 lots of x plus 4 now. And then we've got this times x. Okay, so then let's just bring it all together. So 9x minus 4. Then then we have 3 times 3, which is going to be 9 again. Then x minus 4 times by x plus 4 times by x. But then I clearly notice the 9 will cancel here, but also the x minus 4 will cancel because it's common to both. So this will go to 1 over x plus 4 times x. Well, that will just be 1 over x plus 4, right? We can just get rid of the times here and just bring the x in front. And now this looks like the form we need, right? X of x plus r. Well, r is just going to be, if you compare, r is going to be 4, right? You don't have to say that, but that's the form we got, so that should be our answer. Cool. So that is the whole idea with these sort of algebraic fractions. You just need to factorize as much as you can, and then things should simplify and cancel out to get your desired answer. And obviously, make sure you add, subtract, multiply, and divide correctly, like with normal fractions. If you do those two things and you factorize wherever you can, then you should be golden. But yeah, that comes up every year. So again, if you want those sort of marks and grades, make sure you do practice it. But yeah, but I've also gone over questions like that before my other streams. I've gone through a couple algebraic fraction questions. But yeah, that's another one. Cool. So then let's have a look at this one. Okay, so we are given a solid frustum. So a frustum is this shape by taking the original large cone, which would be here, by a smaller cone, which would be there, right? And the surface we've got left, the solid is a frustum. Anyway, so this frustum is made by removing a smaller cone by a large one. Yeah, so that's what I just said. At the slant height, which is going to be here, and you can see by the diagram, it's also there. You will always be given the formula for this sort of stuff. And the slant height is 6 here, and of the small cone, and the large cone, the slant height is 10. The radius of the large cone is 3, and it's all given on the diagram, right? And then it says to calculate the total surface area of the frustum. Okay, so with this sort of question with frustums, you need to consider basically the large cone and the small cone separately, and then you go from there. So I'm going to need firstly the surface area of the cone, but more specifically, uh, it's asking about the curved surface area. So firstly, we're going to need to work out the curved surface area of the cone. So which cone? The big one, right? Let's do the big one first. So curve, and we're just going to say SA, surface area of the big cone. So remember, the big cone is going to look like this. So that's going to be your 10 with the slanted height. The radius of 3. Very awful drawing, but I hope you get the point. And yeah, then we can use this formula here. So the curve surface of the big cone, that's going to be, well, pi here times the radius of 3 times by the slanted height, which is 10. So that's going to be 30 pi. And the good idea is just leave it in terms of pi when you can. You know, we'll deal if we need to if we need to use pi 3.14, we'll deal with that. But leave it in terms of pi to get the exact answer. Okay. I don't like this. I'm going to get rid of this now. Very bad drawing. So that's the square over the big cone. Okay. Um. Well, then you should notice, well, then the curved surface area of the small cone, then, because we're going to need, again, you're going to need to consider the big and the small cones separately. So let's consider the curved surface area separately. So then the small cone is going to be this bit here, isn't it? That we chopped off. So then if I draw it, then let's draw it here. Looks like a nose. Well, we know the slanted height is 6, but we need to know the radius in order to use the formula. But the radius here is not going to be 3, because you notice the circle base here, is not the circle base on here. It's smaller, so the radius is going to be different. Well, how are you going to find that radius then? That radius here. How are you going to find it? Well, you should notice, essentially, we just chopped it off, so it's going to be similar. The small cone is going to be similar to the big cone. What that means is there's going to be a scale factor between them. So that means all their lengths will differ by scale factor. So there's time to work out the scale factor. But we know there's the slanted height on both of them, don't we? This 10 is for the big cone, and the 6 here is for the small cone. So therefore, the scale factor to go from big to small is going to be 6 over 10. And that's going to be 0.6, right? So therefore, the radius of the small cone is going to be radius of the big cone, which is 3, times by the scale factor to size it down, okay? So 3 times 0.6 is 1.8. And that is, again, the key idea with these sort of Frustum questions. So firstly, you consider this big and the small cone separately, but also the fact that cones are similar, so they will so there'll be a scale factor between their lengths, okay? Like with any similar shape, okay? And yeah, so the radius will be 1.8 then. So therefore, the small cone then is going to be then pi times 1.8 times 6 for the slanted height. So that's going to be, put that into the calculator, 10.8 pi. Okay, cool. Okay, so what is that giving us? Well, it's giving us the surface here. This whole surface. But what it's not giving us is the circular base, the area of the circular base. Imagine if we held this sort of cone up in the air, up in the middle of the air. We would also be able to see from below this circular face, which is also a surface, right? So that would be the surface area of the base, right? The curved surface area gives us everything else, right? The surface that's curved. So then the total area, the total surface area, would be the curved bit and the base here, okay? Which would be a circle, so it'd be pi r squared. So what that's telling us, well, the frustum, it has this curved bit here. Oh, no, sorry. Here, but also it has a circular top and circular bottom. So the curved surface area of the frustum, firstly, well, it's going to be the big surface area minus the small surface area of the curved. So it's going to be 30 pi minus 10.8 pi. And that's going to be 19.2 pi. But that's the curved bit, right? Then we need to consider the circular base on the top and bottom, right? Well, that's going to be the area of the big circle with the radius of 3. Add the surface with the radius of 1.8, right? The radius 1.8. So therefore, the big circle, I should call it, on the bottom, the area is going to be pi r squared, but the r is 3, okay? So it's going to be pi times 3 squared, which is 9 pi. And so the area of then the small circle, which is here, right? The circular face on the top of it, is going to be pi times 1.8 squared, because the radius of the small one, remember, we worked out was 1.8. So it's going to be 1.8 squared, and that will be, because remember, also, I'm doing this because the area of circle, remember, is pi r squared, the key formula. And so that's going to be 3.24 pi, okay? So therefore, the total surface area then the frustum. Well, it's going to be this curved bit, first of all. This whole curved bit. Oh, for God's sake. Here. Which is obviously the curved surface area of the bigger cone minus the curved surface area of the smaller cone. But we worked it out. It was that would have been 19.2. So this 19.2 represents the curved surface area of the frustum by taking away the bigger minus the smaller cone. But then we have these two circular faces on the top and bottom. So the big circle is at 9 pi and the small circle is 3.24 pi. And so then we just add them together, right? And 9 pi. And that will get you an answer of, oh, for God's sake, 19.2 pi. Add 9 pi. Add 3.24 pi. And actually, it just gets you a decimal. That's why I was bugging out, because it doesn't give you it in terms of pi, it just gives you decimal. But that's fine because it asks you to give it three significant figures, so we need to round it anyway. So the decimal answer of this is 98.777167, blah blah blah. And it's an area, so it's going to be centimeters squared. But we need to round up three sig figs. So 98.8, right? Because 1, 2, 3. And then the 7 will round this up to an 8. And that being centimeters squared to 3 sig figs. Okay. So that's the whole idea of a frustum. Okay. And actually, I think this is a harder question because it's asking for the surface area. Usually, they like to ask about the volume, which is a lot more simpler because of the fact that really it's the volume of the frustum, well, the space inside of it, right? It's just going to be the volume of the big cone, which again they give the formula for, minus the volume of the smaller cone, and that's it. But because of the fact we're chopping it off, we have these faces on the top and the bottom, so we have to consider those surface areas as well. So we just have to extend it a little bit more for surface area, but the whole idea is essentially the same. The curved surface area, we have to take the bigger one from the smaller one, and then we need to factor in the surface area of the small and the bigger uh, circles on the top and the bottom, those faces as well. And so therefore we should get this answer at the end. But yeah, again that'll probably that'll probably come up. I think a frustum question like that. Okay, question 20 now. And again, this is a circle theorem question. Hopefully, you can spot it is going to be a circle theorem one. Again, that will come. It'll definitely comes every year, and it hasn't come up yet. Yeah. So let's just have a look at it. So A, B, C, and D are points on a circumference on a circle, center O, and we're given a straight line. So they're giving us all everything on the diagram, right? Then we need to work out the size of angle CDE. So the best first step is first just to label where the angle is going to be. That'll help you guide to what you need to work out. So CDE is going to be this angle here, and I'm just going to call it X. So then, once we've done that, work out what we can do immediately, and it should mostly stare at you. Um, so we're not given anything with tangents, so that rules out the fact that we consider a radius and a tangent being perpendicular. It rules out alternate segment theorem. We don't really have two different segments either, so we don't have the same segment theorem. So that really does whittle down to what we can consider. But notice, well, actually, we have an angle at circumference and an angle at the centre. So what's staring at me immediately is that this angle is going to be 32. So I'm going to say angle, and that angle is going to be BAD. And that's going to be 132 divided by 2, right? And that's going to be 66. So then I can label that 66. And we have to show a reason for every step we do. So that's going to be because since angle at center is twice the angle at circumference. Okay, cool. Okay, so what can we do now? Like I said, we are quite limited in what circumference we can do. Well, the only really other one I think is the cyclic quadrilateral one, and actually we do because we have all these different points on the circumference, and actually, when you have in general 4 different points all on the circumference, say here, here, and here, if we then connect all of them as so to form some sort of quadrilateral, a cyclic quadrilateral in a circle, where all the vertices on the circumference. That then we can deduce stuff like the angles, that the opposite angles have to add up to 180. Well, actually, I noticed we do have a cyclic quadrilateral here. Now, it's not going to be this one because of the fact that whilst B, C, and D are on the circumference, O is not. So it's not a cyclic quadrilateral there. But A, B, C, D is. Right? So if I just again label that, so A is here, B's here, C's here, and D's here. Then this is a cyclic quadrilateral, and we know this angle here. So the other thing I can work out is that this angle here, so angle BCD, that's going to be 180 minus 66 because again it's an opposite angle because they're facing each other. But also because of that, and in the cyclic quadrilateral, they have to add up to 180. So that will give me 114. And the reason for that's going to be because since opposite angles in cyclic or cyclic, it depends how I don't really know how you pronounce it. Quadrilateral, I have to squeeze it in there. Add up to 180. Okay, so now we know that this angle here, BCD, is 114. Well, what else can we work out from that, right? Well, notice this angle as well, which is then getting towards x. But this angle is on a line. So therefore, this other angle then, DCE, that's going to be 180, take away 114, right? And so that's going to be 180 but take away 114. That's again going to be 66. And the reason for that is going to be actually spot. We have 2 angles here on the line. Oh, here. So then, if this angle is 114, oh, for God's sake, no, don't move. Okay. So if this angle is 114, so that one's going to be 180 take away 114, which is now 66. And the reason is since angles on the line add up to 180. Okay. But that's not sucker for him, but it's still something you need to write down, right? Because it asks us to give a reason for every stuff everything we calculate. Okay, but okay, so what can I do with that now? Well, I noticed, well, we have a triangle here, right? D, C, E. And I know 2 angles in the triangle, and this missing angle X is the last one. So therefore, angle CDE is X, and that's going to be 180, then take away the other 2 angles. The 16 take away the 66. And so that's going to be 98. And then the reason for that's going to be since angles in a triangle add up 280. Okay, and then we've got our angle x. So again, that's always the idea with these sort of circle theorem questions. So once you know where your angle, missing angle is, what you need to work out, then work out circle theorems and things you can immediately work out. Like I said here, in this case, I immediately know we have an angle at the centre. And then I saw that we have a cyclic quadrilateral there, right? And then I could work out this angle, opposite angle. And then I know we have a straight line here. So then I worked out the 66. And then I found x because it's in a triangle. Okay, and that's the idea, right? So you go, and so you know one thing at the start you immediately can work out. So a circle theorem you can immediately apply. And usually, like I said, it's quite obvious. If we said, look, there's a tangent, you're probably either going to need a radius and a tangent perpendicular, or the alternate segment theorem or something like that. And then you can work out every other angle you can work out from that, and then eventually you get to x, right? But yeah, so work out basically the whole strategy is work out every angle you can work out, right? Go step by step. Eventually, you'll be able to solve and get the missing angle that you want. But yeah, cool. Question 21 now. So again, they might ask you to do something with trig graphs. They might ask you to sketch it. They might ask you to do something else with it, but you do need to know them. So we're given a sketch for tan of x, and hopefully you should recognise this. The graph of tan of x is translated to give the graph y is g of x. So this is not g of x, by the way, this is tan of x. So it says, following the translation, the point Q here moves to a point R. The point R has coordinate 90 minus 5. So this is tan. Where is 90 minus 5 going to be? But 90 is firstly on the asymptote here. So that's x is 90. So then minus 5 is going to be about there, isn't it? And that's going to be where R is. Okay. Okay, so we need to find an expression for g of x in terms of x. Okay, so it's telling us it's been translated from Q to R. So we need to work out the translation, right? What the vector is. So that's going to be looking at x, y. So how many units are we moving in the x direction? So how many units to the left? And then how many units are we moving down in the y direction to get to R? And that's a translation, right? You're just moving units to the left or right and down and up. Okay, so obviously to work that out, we're going to need to know what Q is, right? And we can work that out just by knowing what the tan graph is. So, I notice it's on the x-axis. So this is at 0, right? But then I note you should note on the tan graph, it repeats every 180. So it gets to the next point at 180. And so this would be at 360 for x, right? And so the point of Q is going to be 360, 0, right? Because then if it's on the x-axis, it's y0. And so that gets translated to then R, which is 90 minus 5. So what is that doing? And how are we getting from 360, 0 to R then? Well, firstly, how many units are moving to the left? It's going to be 360 minus 90, right? And that's going to be 270. So, and because we're going to the left, we're subtracting by 270. So it's going to be minus 270. And then what about the y? So it's going from 0 to minus 5, right? So it's going to go down by minus 5. Okay. So if we're going down, well, we're going below below the y axis. So it's going to, well, so if we're going in the down direction, it's going to be more negative, right? Because if you go down the y-axis, you get a smaller number. So it's going to be minus 5. Likewise, if x, if we're going on the left, that's going towards the negative x axis, right? So it's going to be a negative. So you should remember if you go to the left, it's minus, right would be positive, and then up would be positive for y, and then down is negative. And that's how we get that translation vector, right? Okay, so we've got what is translated by then. So what it says to find the expression for g of x. So g of x is this transformation, right? This translation. So what's it's effectively saying is, if we have tan of x, we need to then translate tan of x by 270, moving 270 units to the left, and then 5 units down. So this is the same as subtracting by 270, but when you have a translation f of x, if you then say f of x minus 270, you do the opposite. So you'd think by this we'd subtract 270 to every x coordinate, but actually it does the opposite. You add in 270 units. So if we said tan x minus 270, you'd be wrong, because actually that would force q to move to the right by 270, not to the left. We want to go to the left, so we need to do the opposite. So we need to say tan x plus 270 to then go that way to the left. Because the fact that if you whatever you do for x in a translation of a function like this, it does the opposite to what you expect. Okay. So we need to add 270 instead. Okay, and therefore we do the opposite of subtracted by 270, which is what we want. Okay, but then you need to go down by 5. So then it's just going to be minus 5 outside. Anything outside the function that affects the y value, and anything inside the function, like we just had, affects the input. So here it would only affect the x coordinates. So here this is saying we subtract 270 to all the x coordinates. If we had f of a half of 2 of x, say, that's saying instead of multiplying by 2 to each x coordinate, you're dividing by 2. And that'll affect the x coordinate because it's in the input. Okay, it's inside the function. Anything outside the function, say if you had 3f of x, that's times in the y coordinates by 3, and it does what you expect. So if you change the x, you do the opposite, like I said. So instead of adding 270, you subtract. But if I'm minusing 5 to the y coordinate outside, it does exactly what you expect. It's kind of the way it works is a bit weird, but you just need to remember, if you translate by x in a function, you do the opposite, and then for y, you do exactly what you expect. So minus 5 is shifting it down by 5, which is what we want to get to r, and that's the translation vector, right? To get from q to this r, and therefore that's going to be expression. So g of x now, which represents this translation, is then just going to be tan of x plus 270. So that's firstly shifting the x coordinates back by 270. You negate it, subtracting by 270. And then you're going down by 5, so you should subtract 5 to the y coordinates. And that is your expression. Okay, very, very tricky question that is, but that is the approach there. Okay. Question 22. For this question, I'm going to read it first, but it says a high-speed train travels a distance of 487 kilometers in 3 hours. I'm going to underline the numbers. The distance is measured correct to the nearest kilometer. The time is measured correct to the nearest minute. By considering bounds, work out the average speed in kilometers per minute of the train to a suitable degree of accuracy. Okay, so the first one I'm going to say, actually, I think this is a very, very, very similar question. Like this will come up in your paper. They haven't asked about speed yet, and they haven't asked about bounds. I've noticed on several occasions they love to mix speed and bounds together. So you need to calculate speed first of all, and you should know it's in this little triangle here. So if we have distance, speed, and time, remember it's this sort of triangle, formula triangle. If we want the speed, we're going to cover that up. So you're left with d over t. So that means speed is then going to be distance over time. And then, like, we can consider bounds of the three to work out the upper and the lower limit for speed. The upper and lower bound for speed, right? Using this. Okay. And so they love mixing the topics together, like I say. So I do think there's going to be a speed bounds question. I really do. So make sure you practice questions like this. I think this would be a really good one to practice. Then it said by considering bounds, work out the average speed. So we're going to need to consider the upper bound for speed and the lower bound. But if we're going to work that out, we need the bounds for distance and time first, okay? But what we're given, we said distance and time are measured to the nearest kilometre a minute. Let's deal with distance first. So they told us that d for distance is it told us it's a distance of 487. But it's rounded to the nearest kilometre. So when you are rounding and then when you consider the bounds, consider the next number. So the next kilometre would be 488. And the number before that would be 486. To get the bounds, you then consider the number in between, right? So it's going to be 486.5 and 487.5. And that is your bound, right? So your upper bound is here, so 487.5, and your lower bound is 486.5. Okay, cool. Okay, what about time then? Well, time is given in 3 hours. However, they said it's measured to the nearest minute. Um, so we're probably going to have to convert to minutes. And actually, look at our answer. They want the answer in kilometers per minute. And that's telling you the distance has to be in kilometers and the time has to be in minutes. So this 3 hours needs to go to minutes. So how many hours? Well, how 3 hours is how many minutes? Well, you should note that 1 hour is 60 minutes. So therefore, 3 hours is going to be 180 minutes. Therefore, the 3 hours just goes to 180 minutes. Okay. And then we need the bounds for that. So then it's saying it's rounded or correct to the nearest minute. So again, 180. Then the next minute is going to be 181. So then the minute before it's 179. So we consider the closest minute right between. Then the bound, again in the middle, is going to be 179.5 and then 180.5. So therefore the bound is going to be 180.5 and 179.5. Cool. So now we've got our bounds for distance and time. So now we can use that to work out the bounds for speed. So firstly, we need the upper bound for speed. So I'm going to say speed UB for upper bound. Well, we need to essentially maximize this fraction here, this division. How are we going to do that? Well, you're going to need to take the maximum value for distance and the smallest value for time. So the lower bound for time and the upper bound for distance. Why is that? Because if we have a division, the numerator has to be bigger and the denominator has to be smaller to make the fraction bigger. If it helps, consider just 2 examples, right? Any 2 examples. Consider, say, for example, 8/4, and then pick a number, a fraction, sorry, with a smaller denominator, say 6, and then there's bigger denominator, which is 3. Which number is going to be bigger? Well, 8/4 would be 2, and 6 over. Oh, hang on, what have I done here? No, they're equivalent. Sorry. No, the numerator has to be smaller. Hang on. No, sorry. 8/4. No, 8/2 and 6/3. So what I'm doing is I only did one of them. So consider the numerator to be if I make the numerator smaller and the denominator bigger. What I did was I kind of made the numerator smaller, but then the denominator smaller as well. No, so, yeah, so it didn't work out. Anyway, so then that would be 4, but then 6/3 would be 2. Okay, that's what I wanted. So I can clearly see then, just by an example, if I make the top number bigger and the denominator smaller, that will give me a bigger result than if I made the top number smaller and the denominator bigger. Okay, that's if you're really struggling to wrap your head around what bounds to pick. You can just pick some. You can just pick some example numbers to see which one would get you the bigger one. And in this case, then, because of that, the upper bound for speed, you're going to need the upper bound for distance, which is going to be 487.5, which is there, and the lower bound for time, which would be 179.5. And then I put that into a calculator. That's going to be this number here, 2.715877,437 kilometers per min. Okay. That's your unit, by the way. And you do have to again give all the digits because this bound is all about rounding and accuracy. So all the digits matter. So we do not round yet. So that's your upper bound. Then what about the lower bound? Well, again, it's a converse argument. If we want to make it small as possible, we need to make the denominator smaller and the time bigger, so the bottom number bigger. Again, pick two examples if you're struggling. Say if you have a fraction again of 8/2, then if we want the lower bound, let's try and make. Then I think well the top number has to be smaller, so let's say 6. And the denominator has to be bigger. So then let's try and increase 2 to 3. Again, you get 4 and 2. So actually, this now is the smaller number. So this will give the lower bound if I make the top number smaller and the fraction bigger. The denominator bigger. There we go. So the overall fraction is smaller. Okay, so that's the lower bound. So that we want the lower bound for distance, which is going to be 486.5. And the time is the upper bound, so we're going to want let's go up here. It's going to be 180.5, and then I put that into the calculator. I'm going to get this number here, 2.695290,859 kilometers per min. Cool. So now we have our bounds. Then it says, because by considering those two bounds, work out the speed to a suitable degree of accuracy. So what that's saying is, to give a value for the speed, the lower bound has to equal the upper bound, right? Because then anything in between the bounds is also going to be the same. So if the speed is consistent, the same all throughout, that is our value, right? So then we need to find out we need to find what number to round to make sure the upper bound and the lower bound agree, so they're the same. And the way to work that out as well, consider when the numbers in the digits start changing. So here, firstly, 2 and 2 in the units is the same. So then let's consider the next part. 7 and 6. Well, then there's a difference, so we have to leave that there. So then let's consider rounding. So the 7, well, the 1 will make it stay 2.7. And then 2.6, well, the 9 is going to round it to 2.7. So actually, they're the same. So therefore, the speed is then going to be 2.7 to the nearest decimal place, or to two significant figures. They're the same thing in this case. So the nearest decimal place, and that's your value, right? And the reason for that is because the upper bound and lower bound are the same to 1 dp, okay, to 1 decimal place. And that's the whole idea, right? Once you consider the two bounds, we want to make sure the bounds are equal to each other. So then you start comparing the two numbers. Then you start checking the digits until when they start change. So when the number changes in a digit, right? So the unit digit 2 and 2 are the same. So then let's go to the first decimal point when the 7 and 6 are the different. So then we need to round from there. Okay, so we need to round the 2.7 and that'll stay 2.7 because of the 1. And then the 2.6 here will round up to 2.7 because of the 9, and therefore they're the same. So because the bounds are the same, then the speed has to be 2.7 no matter what. And so therefore that's our value to two separate decimal places. And that is the whole idea with that sort of question, right? And like I said, that is really good going over and, doing those sort of questions, especially with speed involved, because I do think this will come up in your paper. Mixing speed together. And also because of that, you need to check your units as well. So like I did here, kilometre in distance, well, it's in kilometres at the speed, but it's in hours and we need it to minutes. So you first need to check to convert it to make sure the units agree with each other, right? And the answers in minutes as well. So that's something you need to be aware of and check. But yeah, that's the whole process of bounds. I don't think that that's scary. I don't know. Once you really, I don't know, wrap your head around it and understand the logic here. But hopefully that kind of makes some sort of sense. With what we've done here, right? And like I said, don't be afraid to try numbers out. If you're not sure if you need to increase or decrease the numbers on the top and the bottom, again, pick some fractions, pick some numbers to test out, and then change the denominator, make it smaller, and make the denominator bigger, and see what number, and compare if it gets smaller or not. Okay, so here it's 4. Then if we made the fraction smaller by decreasing the numerator and increasing the bottom number, the denominator, that gets us 2. So it has to be a lower bound, right? If we do that. Okay, cool. Okay, and this is the final actual question. There is a challenge question, which I'll talk about in a minute. But yeah, this is the final question. And it's a vectors one. And again, as much as people don't like vectors, it is going to come up, right? And this is a very nasty one as well. So I'm actually going to leave it for a few seconds and then hopefully, well, try it and do it yourself or something. And then I'll go over it. Okay, so we're given OAB is a triangle, OPM, which is here, and APM are straight lines. A is the midpoint of AB here. OA is A, so let's label that. And OB is B here. We're also given this ratio of OP to P to M is 3 to 2. Work out the ratio of ON to OB. Okay, so I'm going to leave it there for a few minutes, seconds. Okay, so what we need to do to consider the ratio ON to NB, we're going to need to consider the vectors ON and NB, right? So let's first consider O to N, okay? And how are we going to start? How are we going to start with this? Well, the strategy with these sort of vectors question is to use what's given. So the first thing you need to consider the different routes you can take to get from O to N. So you can't go directly, obviously, because that's just O to N. That doesn't tell us anything. So let's consider an indirect route, a different path we can take. And you can use the question information to guide you. So we're given this ratio here, OP to PM. So we're going to need to consider the vectors O to P, for God's sake, O to P or P to M, okay, in our answer. But I'll notice I can go from O to P and then P to N, okay. So I think that's going to make, I think that's going to be a suitable path to take. OP and then P to N, okay. Well, I'm given first, so then I need to work out these sort of vectors, right? Well, O to P, well, we're given OP to PM is 3 to 2. But OP and M lie on OM, right? So OM is OP, add PM. Now, actually, if we add these parts together to 5, isn't that just the whole line OM? What we can do instead then with these sort of ratios is Well, actually, let's say OP is going to be 3/5 of OM, right? Because 5 in total has to equal OM. So if OP is 3 lots of 5, then we can say this. Okay. And yeah, so then we can't work out OP really, but what about OM? I think we can, um, because we're given some information, because we can go from OA to AM. Um, and we know stuff about M as well, because it's the midpoint on AB. So let's do that. So 3/5. So then I'm going to say OM. I'm going to do that. When am I going to do that? I'll do that here. No, actually, I want to make room. I'm gonna. I'll tell you what I'm gonna do. I'm gonna say I'm gonna bring the OP over here. 3/5 OM because we're gonna need to make room for this ON. Um, so then let's find OM. OM. There's N's and M's, so it's gonna be quite hard to distinguish. O to M, like I said, is gonna go from O to A. So again, I'm gonna find a path to get to there. O to A and A to M. Okay. And again, I want to use the question information. So I'm given M is a midpoint, so I'm going to need to consider AB, okay, which is A, and then because AM is half of AB, so it's going to be OA add a half A to B. Okay, so OA then is A here, so it's going to be A, and then a half of AB. What's AB? Okay, so A to B this way, we can go from A to O. So that's going to be minus A then. If A here is positive that side, if we go the opposite direction, it's minus in. So it's going to be minus A, and then we go from A to B, O to A here. Then we can go from O to B, which is B, and that's AB. And now let's get rid of all that. Cool. And so then to work out OM, we can just simplify this. So it's going to be A minus a half A, which is times out by a half, and a half B. Um, so the A minus a half A is going to be a half A, positive a half A, add a half B. Cool. So that's OM. Now let's go up. So now we know OM, then we can work out OP over here, right? Which is one of the ingredients for ON. So then OP is going to be 3/5 of a half A, add a half B. Then if we times it out, so 3/5 times by a half is going to be 3/10 A and 3/10 B. Okay, cool. So now that's OP. We now need to find some way of getting PN. Okay. Okay. So PN. So the issue is with PN. If we went from here to P to N, and then say from M to B, and then B to N, that like that's not really gonna give us anything because we already used this ratio part to on PM. We already used it to work out O to M, and we already used it for OP even. So if I went that way, I'd be using the ratio, and I don't want to use the same sort of information really, because then it'll basically just cancel out to the length, and eventually you probably get ON is equal to ON, basically, if I keep reusing the same information. So I need to again come up with a new way of getting using another bit of information. Okay, well I can't go from P to N directly because that's what I'm working out. So then what if I went from P to A to B, and then B to N? Um, Again, that's not going to work. Um, because of the fact that really now we're going from B to N, but I want to N to B. And I want to avoid that because we don't know what that is yet. So then really left from P to O, and then what, O to N, but then that's just basically undoing all of this. Okay, so the long way really is to then we need to look at the information again. Anything else we're given? OAB is a triangle, that's not going to help. But we're given this. OPM and APN are straight lines. So we want P to N. That lies on the straight line A to N, does it not? So therefore, I think we can use that fact, can't we? And you should know on the straight line, say if 3 points ABC on the straight line, they're all parallel to each other. So if we make two vectors, any vectors out of them, say AB, that's going to be some multiple of AC or BC, right? Because they're on the straight line here, you notice they all have the same direction, so they're going to be parallel, okay? And that's what it means to be parallel. If 3 points on the straight line, they all the vectors you can make between them are all going to be parallel. So what does that mean then? So P to N. Wow, I notice P to N is again on the line AN. Well, so I can then either say A to we can say P to N is some lots of A to N. But the problem is I'm not going to get an explicit answer for that because how am I get okay? So if I go from A to N without going to P, because that would defeat the point. How am I going to get away? How am I going to find a way of going from A to N without trying to go from O to N? And then obviously that defeats the whole point because we want to find ON or NB. We can't, can we really? Because N lies on OB. So we're going to have to go from O to N or B to N, which we want to work out what either of them are. They're both unknown. So we want to avoid going that way from A to N. So we can't use A to N essentially because of the fact we're going to need to use ON or NB to find A to N. So the only other way is instead recognizing that P to N is also going to be parallel to A to P. Now to get from A to P, we don't need to go to N. We can just say A to O and then O to P. We know both of those vectors, don't we? So we can say Pn is going to be some lots of AP, okay? Again, because AP and N are all on this straight line here. And so A to P, and they're going in the same direction, they're going to be multiples of each other, right? Which is where this comes from. So now we need to then find a way of getting to A to P. Okay. And there should be a way of getting an actual vector for it without having to go to O, N, or B. So we don't have any unknowns, okay? So A to P, then, let's do that here. A to P. Well, how are we going to get from A to P? We can go from AO. So again, if O to A is A that side, then to go backwards, it's going to be minus A. And then, once we go from A to O, we can go for O to P. But we know what OP is already. We've worked it out. O to P is here. It's 3/10 A and 3/10 B. So we're good. We've got an actual vector for it. So it's going to be minus A, add 3/10 A, add 3/10 B. So then minus A plus 3/10 of A. That's going to be minus 7/10 of A. Add 3/10 B. Okay. And that is your vector AP. So therefore, P to N then is going to be K lots of it again because of the fact it's parallel. So it's going to be K lots of minus 7 over 10A, add 3 over 10B. So therefore, that'd be minus 7 over 10K lots of A, add 3 over 10 k lots of b. Okay, now we can substitute OP and PN in. So ON then is going to be, well, OP first of all, like we said, was 3 over 10a, add 3 over 10b, and PN is minus 7 over 10 ka, add 3 over 10 kb. Cool, okay, but the only problem is, if we want to find this vector, well, we need to find what k is. So then what we need to do then, again, we need to consider what else we are given. Okay, is there another, and the strategy is we have to find multiple ways of expressing the same vector. But this is one way. But we've already used all the information so far. We used the fact OPM's a straight line. We used the ratio. We used OA and OB. We used the fact M's a midpoint. We used the fact APN is a straight line to find out AP. We've used all the information, so any other way of getting there really is not going to lead us anywhere because we used all the information already. What else can I do? And this is where you need to recognise, well, we have another parallel line. We actually know ON. Again, we can form a ratio of ON to NB. Well, that's going to be some ratio, right? Something we don't know. But it lies on OB, right? Therefore, and we can see this clearly, ON is going to be parallel to OB. And we know what OB is. It's B. So therefore, ON, again, is going to be some T, lots of OB, right? Because it's parallel to ON, remember here, is going to be parallel to OB. Hopefully you can see that right. Let me try and make it a bit more clearer. So ON here is it's an OB. They're on the same straight line, right? Here, ON and B are on the straight line. So like we did with AP and PN, they're parallel vectors. And we know that OP is going to be B, so it's going to be T lots of B. So it's parallel to the vector B. Therefore, we can then, let's get rid of this part now. We don't need it now. Let's get rid of all this. If we then say, well, we found another way of expressing ON, and that's going to be equal to TB. Now there's two unknowns, so you might freak out, but actually we can compare because we've got two vectors as well, two different vectors, A and B. So now we can just compare to find these missing numbers K and T. And then if we found that, well, we can work out ON. Exactly, can't we? And then we can go from there. Let's solve it then. So if we compare, firstly, we can compare the A bits, so the A component vector. So that means 3 over 10 minus 7 over 10 K, lots of A. Well, there's no A's on here, is it? It's almost like saying 0 lots of A. So that's going to be equal to 0, right? So you set all the A components equal to each other. Let me get rid of this. Again, just make some more space, make it clearer. Okay, well then, if we solve this, then that's saying 7 over 10k is going to be 3 over 10. Well then, therefore k, if we then divide by 7 over 10, is going to get you 3 over 7. Okay. So you solve for k here. So if I want to get rid of 7 over 10, I divide by 7 over 10. Okay. Cool. So we found k, but now we can also compare the b parts as well. So then I can so I'm saying so that's a, right? Therefore, to compare the b component, then, well, again, 3 over 10b, so it's 3 over 10 here, plus 3 over 10k b is going to be equal to tb. Okay, but we know what k is, don't we? So t is 3 over 10. add 3 over 10 lots of k. K we just worked out to be 3 over 7. So therefore, then I'm going to get rid of this bit now to make more room. So then therefore T, you put that into the calculator. Funnily enough, weirdly, this was on a non-calculator paper, but it can very easily be on the non-calculator. These are nasty fractions for a non-calculator paper. Anyway, we have a calculator, it's paper free, so we can just use a calculator. So then 3 over 10, add 3 over 10, lots of 3 over 7, gets us 3 over 7 for T. Okay, hang on. I want to check because I don't think they should be the same. It doesn't really make sense. Minus 3 over... OM. I think I need to check my answer here. 3 over 10, B, minus 7 over 10. Hang on, let me check. It just doesn't make sense as the same. Does the same. I don't know. Don't know. I don't think I've done anything wrong. I'm just okay. I'm just gonna assume it is. I just find it weird that they're the same. So normally that might be a wrong answer, but I don't know. Let's just go ahead. So therefore, that's saying then. 'Cause remember ON, we have this bit, but ON also equals TB. Okay. So ON equals TB. Well, that's going to be 3 over 10th, 3 over 7th B. We have an actual number, we have a vector. Well, actually, think about what that's saying. This is going to be 3 over 7B, but it has to go to B in total. So that means this NB is going to be 4 over 7. Therefore, the vector ON to NB is going to be 3 to 4, right? Hopefully you can see that because there are 7 parts in total. So if ON is 3 parts here, therefore NB is going to be 4 parts. And the whole of 7 will go from O to B. So that is your vet ratio. And I've just checked that is actually the right answer. Okay. Oh, there we go. Oh man, what a nasty vectors question. Oh my lord. Okay. Yeah, so that's the final main question done of the pack. Yeah, so like I said, I did two. This is the second part now. So the 2 parts were I said the first part yesterday, the second part today. I think I'll upload this part separately in case people want a shorter version of just the harder questions to practice, but I'll also do a whole because then if I do it part 1, part 2 together, it goes then from question 1 all the way to question 23 here. It'll be basically a paper 3. essentially. It would look like paper 3, right? So I'll do that as well. People want to practice like almost like a practice paper, I guess, or a look through a practice, meet someone to explaining and going over a potential paper 3 paper. I'll do it in that way as well for YouTube. But those are the main questions done. That is a nasty final question. There were some hard ones here. The tan graph here, the vectors one. The Frustum one could be quite tricky, maybe. I'll tell you the one I struggled with the most, though. I'll tell you what. It's question bloody 2. Remember if we watched part 1? This one, the bloody nets. Not the nets, the plan and the front elevation. Ugh. I know, Mike's. Oh no, I do apologise again. My explanation for this was really, really wishy-washy. It's just something you have to visualise. It's hard to explain. But I don't know. Maybe I'll try and explain it again roughly. But the plan is saying that this is going to be a width of 3 squares apart, and the front elevation means this height here we'd see from the side here. It would have a height of how many squares? 5 from the base to the top, and we would see it go by 3. So here we can see it's 3 by 5. So a height of 5 and a width of 3. And these little sort of lines indicate where the you know, when the lines start creasing because of the bendy, the lines change. So here, this is a straight line, so that'd be fine. But here we changing lines, so there'd be a crease after the first, after one square up, and then when you were 3 squares up here, that's where we have this jump, this gap, and then we get another line. So that represents like a crease, you know, if you will, and then it goes up there. And that'd be hard, but there are lenient. You don't need to draw these lines to represent like the fact you're changing from one line to another. You can just draw a box of 3 by 5 and you'll get both marks. But yeah. But actually, I did say there was a little challenge question, which is here. So I'll leave it there for people to read and go over. But I did say it at the start of part 1, and I'll say it again now. They have, they can ask one of those nasty geometric circle questions like they've done in the last few years. They might ask it on the paper, and there's not much I don't think me or many other people can do to prepare you. I, I guess rather than just give you these questions, but the thing is, you just need to be better. You just need to be really proficient at all the other geometric topics. So you need to be really confident with areas of sectors and arcs. You need to be able to spot a sector. You need to be able to consider triangles, equilateral isosceles triangles. You need to perhaps consider the circle theorems, how you can get different angles, um, and potentially either angles and parallel lines, like we did earlier. Circle theorems. What's the other one? Uh, Area, arc of a sector. These 3 topics, which have not been assessed yet, I think they could actually merge all 3 of them together to get a really, really nasty circle question at the end. And maybe some other stuff as well. So I'm just gonna warn, but hopefully that doesn't happen and you get a nice final question. But I'm just gonna throw the warning out there, and that's why I've given this question at the end here. So hopefully you had a look at it. So let's see how we would approach this challenge question. By the way, this was a past paper question. It's at the very end. Um, and yeah, let's have a go at it. So we are given A, B, R, and P of 4 points on the circle with centre O. A, O, and R are 4 points on a different circle. So you have 2 circles overlapping. The 2 circles intersect at A and B. CPA, so these 3 lines here are all straight lines. Prove the angle CAB. So let's work that again. So this angle here, CAB, let's call it X, is equal to ABC, which is going to be here y. Okay, so we need to prove those two angles are equal. So where are we going to start? And that's probably the hardest thing with these sort of questions, right? Is where to start. Okay. So again, like with the other questions, especially like the circle theorems and the geometric stuff, work with what you're given first. So here, we are given 4 points on the circle. What do we know about 4 points on a circle? Say here, 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 and here. It doesn't matter where, but what do we know about 4 points on the circle? And if we connect them, they form a cyclic quadrilateral, which we actually did earlier. Why is that useful? Well, we can deduce stuff about angles, can't we? Because we know the opposite angles are going to add up to 180. So we can go from there. Okay. And so actually, we are given two different sets of points. So we have two different cyclic quadrilaterals, right? So the first one is A, B, R, and P. Let's plot that. So A is roughly here. B is going to be there. R is here. Actually, I should make it a bit more representative. So let's draw the circle again. Oh, it's a rubbish circle. Okay, so A is going to be about there. B is going to be there. Here. R is going to be here. And P is here, right? And remember, this lies on this circle here. Okay, with the center O here. Again, it's quite hard to visualize, and you really just have to break up the different shapes we've got, right? The two circles and the triangle and whatever. If we connect, we get this sort of quadrilateral, right? And what do we know? Well, we know from A to P and then A to B, again, it's going to be this angle X. And we know from B to R is going to be this angle Y. So that might help tell us something. They're not opposite, so we can't deduce. Well, I'd hope they're not opposite because then those have to equal. They wouldn't equal each other. But that's one cyclic quadrilateral. Then what about the next one? Because we're also given this information here: A, O, R, and C. So again, let's plot that, and that's going to be for this circle here. Okay, this the left one. So A is going to be about there. O is going to be like there. Then R is going to be there roughly, and C is about there. And then if we plot that, oh, we get this cyclic quadrilateral here. Okay, and then this is going to be A to O. This is also going to be angle X, right? But that's not going to be angle Y because Y is at B here, not at R. But here we're at R. So we only know stuff about X here. So those are the two things I can deduce right away. So those are cyclic quadrilaterals, but we don't know anything with the other angles just yet. We need some sort of other angle to work this out. So let's see what else we have. Well, I noticed we are specifically told about the origin here, the center, and I also noticed we are given the diameter. Um, right. Um, but actually, I can't deduce anything about that because, well, not really, because we're not given anything about tangents or anything like that. Oh, but what do we know? Actually, we can. What do we know about a diameter? It forms a semicircle, doesn't it? What do we know about a particular angle in a semicircle? We know that it's gonna be a right angle somewhere. So we're given a diameter, so then we need to sort of construct a triangle. So these 2 points B and A have to meet somewhere in the middle. Well, on the point of circumference, say here, and then that would give us a right angle. But we need to be really careful where we pick. Okay, so what would be the best place to pick? um, but I think it's probably going to be R, right? Because I know about R here and here. That might help me maybe. So if I then say that A goes to here and B goes to here, I get a right angle triangle, right? We get an angle in a semicircle. Because then the two, remember this, the angle at the semicircle theorem, if we have a diameter, say here, that goes through the center, if then at these 2 points at the of the diameter, if they then both then further meet, right, they meet at another point in the circumference, they form a right, well, it's probably not the best drawn one, but it makes a right angle, okay? So therefore, if we could say B to R and A to R, so they're both ends of diameter, me to R, that's telling you that this angle is 90, okay? Right, okay. Okay, cool. So what can we do with that? So now we have one angle here. What can we do? And consider these. Well, again, notice we have to see. I'm going to use the cyclic quadrilaterals now, I think. So again, A to P, which is there. I have to draw it. And then P to R is oh, there we go, nice. And then P to R is going to be there, and then R to B is here, and then A to B is here. Well, then I noticed that remember A to R then. So remember, if we draw on the diagram, then remember A to R. This bit is a right angle, but I also know this angle in terms of x. Then right, this little angle here. So let me draw that again. Oh, for God's sake. A to B, B to R, B to P, and B to A. Remember how we're drawing the diagram here? Directly from A to R, so here, makes a right angle, right? But then, but I know something about the opposite angle in total. If I know that angle then, what is it? Uh, that angle, yes, yes, the angle ARB. Well, firstly, that's going to have to equal 180 minus x, right? And that's going to be because as opposite angles in a cyclic quad. Relateral, add up to 180. Okay, cool. Okay, so we have this in terms, so we have the whole angle in terms of x. So that's this whole angle here. Okay. But how's that going to help? No, sorry, so this is going to be 180 minus x. There we go. I haven't drawn the diagram the best. This bit will be 180 minus x here, right? Not the whole angle, sorry. This is because here, hopefully you can see if x here, then the whole angle R to O is 180. But then obviously this will go to B, then this will be a right angle. Tricky one again. AR, that would be ARB, would it? No, ARB would be 90. No, we want AR to C. That would be 180 minus that. AR to the P. Hang on, I'm confused myself here. That let me just get rid of all this mess firstly. So we know that's going to be X and that's going to be Y. If we then we know then A straight down here to R is going to be 180 and 90 because that's in the semicircle. Okay. So this cyclic quadrilateral X. So if I draw the cyclic quadrilateral, look like that. So then the angle X is this whole. 180 minus X. I think my drawings are just a bit bad. I think it's not allowing me to visualize it as best as possible. X. So if I draw it again here, say A to R. Okay, let's do this cyclic one, A to O. To R to C, and let me draw it. So that's going to be X, and this is going to be therefore 180 minus X. But then we have B here, and that's obviously going to be another line here, and therefore the rate this goes to R. Oh, but I know this angle here. If that's 180 minus x, because it's an opposite, so that'll be angle AOR. No, oh, sorry. No, this 180 minus x is going to be CRO. Okay, here. C to R to O. Therefore, angle OR BRO, that's going to be that's going to again be 180 take away 180 take away x, right? Because it adds up to 100. It's on the straight line, right? So then that's 180 take away 180, 0, but then minus minus x is going to be positive x. And that's going to be because angles on a line add up to 180. So therefore this angle's x. Okay. And so therefore what we've got, this triangle orb then, OBR. So this triangle here, O to B to R, if I plot it, it's going to look like this. So then we have X, this is Y now, and O is here. So we need to prove that essentially then, I guess Y then here would have to equal this angle X. So that means two angles in the triangle have to be the same. So we need to prove it's isosceles, right? But actually we know it's isosceles because this is a radius, right? So I'm drawing this situation here, let's say. So what I've done here is I have this cyclic quadrilateral here, A to O to R to C here. So therefore this angle was 180 minus x. Therefore this angle would have been 180 take away 180 take away x. That would just be x. That's what I've got. Then I'm left with this triangle ORB. But this triangle is going to equal this triangle, isn't it? Because this side, sorry, because this is a radius. Because it's going from the center to the circumference. Same as this O going to R. Let me get rid of this drawing a little bit now. O to R again. R is on the circumference of the circle here. Same with B. R and B are both on the circumference of the same circle. So that means O to R is going to be the radius R. Same with O to B. And actually, these are then the base angles. Okay. So then I'm going to say O to R is equal to O to B as both are radius of the same circle, right? Therefore, triangle, well, I don't need to say that, but actually, therefore, angle, BRO equals angle, OBR, right? Which is this angle Y here, that be here. And that's going to be because since triangle BOR is isosceles, right? So these two base angles are the same. Hopefully you can see that. Therefore, because we call the BRO, angle BRO is X and angle OBR is Y, therefore X is Y. That's our original, because remember we called x. So I should have said, let x be angle CAB and y be angle ABC. That's what we did at the start. That means the angle CAB is then equal to angle ABC. We did. Good. But see, that's the whole thought process, right? Like, it is tricky. But see what I did there. I considered all the information I was given, which wasn't a lot really. Then I considered, well, they're really emphasising there are 4 points on the circle. What do I know about that? Well, it's going to be cyclic quadrilateral, so I'm going to need some sort of like construct some sort of quadrilateral, right? And then use the fact the opposite angles are add up to 180, which is what I've done here. So this was x, therefore constructed a sort of cyclic quadrilateral here to then say this angle here is 180 minus x. Then I could find this angle here, which would just be x again, because you take away from this because it adds up to 180, which then just gave us x, the angle BRO. And then I just deduced, well, if I need the x and y to be equal, because remember, x was CAB and y was ABC, and we need to show they're equal. How are we going to do that? Well, it needs to be, we have a triangle, so it has to be isosceles. So therefore, I need to consider how two sides, and in particular, it would have to be these two sides, right? For these two base angles to be the same. Well, they're a radii, so they're both equal. So therefore, we did it. So yeah, that is wow, that is tricky question that is. But yeah, um, we got there in the end. So yeah, I guess I'll just make the diagram a bit clearer one more time because there's a lot of mess on there now. So what we did, well, obviously we said that was originally x angle CAB, and this was y angle ABC. Then I considered the quadrilateral from A to O, and then O to R, and then R to C, then and then C to A. Therefore, this is an opposite angle. X is opposite to this angle, so that would be 180 take away x. Therefore, this angle here is 180 take away 180 take away x. That just goes to x. And therefore, got this triangle here. O, B to O. This triangle here. O to Y. OB to R. Um, which was here. So that was x and y. And therefore that's a radius of r, and that side's r as well, because they're both radii, because it goes from the origin O up here to the B and R, which are both on the circumference. Therefore it's an isosceles, so therefore angle x is angle y, which means these two angles are the same. And there we go. Wow. So hopefully you get the thought process right. These sort of really tricky circle questions that might be at the end. You just got to think about essentially, what can I do with the information? What can I construct? What sort of shape can I construct, or whatever, or what property I can use? You know, and like I said, they emphasised a lot about 4 points on the circle. So I'm going to need probably some sort of cyclic quadrilateral. And what do I know about that? Well, the angles, right? And therefore, I can use the angles in some way to then get what I want. But yeah, that is the thought process. But it's very, 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 very tricky question. You know, they're intended. They're for the top of grade 9. You know, that they're meant to be quite tricky. But yeah, that's sort of the thought process, right? But hopefully that's some sort of help. But I am going to leave that there then because we wrap this up. But yeah. Um, what do I want to say? That's it really. I'm going to upload this onto YouTube. Again, I'm going to do this part 2 separate, and then I'll combine them, part 1 and part 2 together. But yeah, but there'll be one more revision session for the night before, hopefully. And then we'll just do some final sort of questions there. Okay, that I'll pick out. But yeah, as for now, I'm going to leave that there then. So yeah, thanks for watching.